I should now like to give a set of 6 problems to constitute an exercise for you to work out, covering the topics that we have discussed so far on the Fourier series. First problem: consider a wave like this, triangular wave this is a voltage wave V1 of t. So, this is a triangular wave, sawtooth wave as it is called, with an amplitude E and period T naught. Find the Fourier series expansion of V1 of t in terms of trigonometric functions. That is in terms of A naught, A n and B n. Repeat this by expanding f t in terms of exponential functions. That is in terms of C n. C find the Fourier series of the derivative of this function dV1 by dt. So, once you take the derivative, you would observe the slope is constant here and slope is constant here, but at this point you have impulses because there is a sudden jump from e to 0. So, it will have, you will have also impulses to deal with. Find the Fourier series of dV1 by dt, and hence the series for V1 of t. So, you do the find the Fourier series of V1 of t by 3 different methods. D, show that the results obtained in A, B, C are equivalent. Compare them and show that they are all equivalent. E, you take another waveform like this. This is E. This is 3E and this is 2E, and the period is T naught as before. That means the waveform is this. This I call V2 of t. deduce the Fourier series for V2 of t from the above results for V1 of t. In other words, what we expect here is you do not find the Fourier series for V2 of t directly, you somehow relate V2 of t with V1 of t. Since you know the Fourier series for V1 of t, you use that information to calculate the Fourier series for V2 of t. That is the first example. Problem number 2, you have a waveform like this. E naught minus E naught, period T naught, take it to be 1 second. This is of course T naught upon 2, this is T naught 0 time t. This is a voltage V of t. Now, if a voltage having this type of waveform V of t is given to an RC circuit containing a resistance of 1 ohm and a capacitor of 1 farad, let under steady state a current IT flow through the circuit. So, this type of waveform is given to this circuit. You are asked to find the Fourier series expansion for I of t under steady state. That is the first part of the question. P, express the power dissipated in the circuit as a sum of harmonic powers. So, the first problem requires you to find out the Fourier series expansion for the current IT under steady state. So, you find out the various harmonic components of V of t, find out the components of current at different frequencies driven by that source and sum them up. That is the Fourier series expansion for I of t. In the second part, you are asked to calculate the power as a sum of harmonic powers. You have two ways of doing this. You know the various harmonic components of the current, therefore, knowing the value of R and the harmonic component of current, you can find out the harmonic power for each harmonic. Alternately, you know the Fourier series expansion for V of t, you know the Fourier series expansion for I of t. So, you can associate the voltage component at a particular frequency with the current component at the same frequency, find out the angle between these two and find out the harmonic power for each one of the harmonics. So, find out the summation, express this as a sum of the various harmonic powers and that will be the total power. This is problem number 2. The third example, let us consider a circuit where we have an input voltage which is a half wave rectified sine wave like this with an amplitude of 100 volts. This is Vi. 0, 10, 20, this is t in milliseconds. That means this is a 50 cycles wave from which we generate half wave rectified sine wave 100 volts. This is the input voltage, and we would like to have a filter, LC filter here, and to try to supply to the load resistance RL of 100 ohms as pure a DC as possible. So this is the output voltage VL. So VL should be a DC voltage to the extent possible, all the ripples should be attenuated. We have a filter which consists of an inductor of 100 millihenries and let us say a capacitor of 1000 microfarads, and the input voltage is this. Calculate the ratio of DC voltage to the amplitudes of the 50 cycles and 100 hertz components in both the input voltage Vi and the output voltage VL. So you have the input voltage, you have a DC, 50 cycles, 100 cycles and so on. We want to calculate these three components of the input voltage and the same quantities in the output voltage, and you should show that the 50 cycles and 100 cycles components are attenuated considerably in relation to the DC when you go to the output. So this is an LC filter. We had earlier in the class worked out an example with an RC filter, show that this is, you will see that this will be a more effective filter than the RC filter. Fourth example, a carrier signal Vc is capital Vc cos omega Ct of a radio station is modulated with a sinusoidal signal of frequency omega s radians per second. The resultant amplitude modulated, this is AM means amplitude modulated signal, is V equals Vc to 1 plus m cos omega st, where omega s is the sinusoidal signal of frequency omega s and this is cos omega ct. So this is the amplitude modulated signal V. Now you are asked to find out A, the fundamental frequency after all this is a periodic waveform because you have got only cosine terms with different frequencies, it repeats itself. What is the fundamental frequency of the amplitude modulated wave? Find the fundamental frequency of the amplitude of the AM wave P. B. The Fourier series expansion of B. Now, if you are clever enough, you could see that you do not have to do any major integrations etc. here. You can simplify your work by combining the cos terms suitably, and you can do this with surprising ease. See, RMS value of V and its ratio to the RMS value of V and its ratio to the RMS value of the carrier. RMS value of the carrier is Vc upon root 2. So, you find the RMS value of the amplitude modulated wave and see what proportion it bears to the RMS value of the carrier. These are the three things you have to find out in this particular problem. One minute. Here I have to give you some additional data for problem 4. Fc you can calculate numerically 1 megahertz, that is the carrier. The signal frequency you take it as 1 kilohertz. Vc to be 20 volts, that is this, and M as 0.8. So, this is the numerical data which you can use to work out the details of problem 4. Okay. You often have heard the time signal that is broadcast by a radio station immediately before the news, pip pip, that type of thing. So, the waveform, the signal will have something like this, So, you have a burst of 1000 hertz signal. We will take this just a data as a typically. Suppose you have a 1000 hertz sine wave which is maintained for 1/10 of a second, and this is repeated every 1 second. That means there is a blank period of 9/10 seconds, and this is repeated, and this is a 1000 cycles pure sine wave. This is the waveform of a time signal. So, we are required to find the Fourier series analysis of this. So, in particular, we are asked to find the frequencies present in the time signal with this waveform. Find the frequency component, particular frequency component which has the largest amplitude. What is its amplitude? So, if you take amplitude of the sine wave as A, what is the amplitude of the component which has the largest amplitude. Now, in doing this analysis, just give a hint, you can put your origin at a convenient location and assume that you have a continuous sine wave. If you multiply this by a periodic pulse train, you can get this. So, a sinusoid multiplied by a periodic pulse train will give this. So, you use that information to find the Fourier series for this. Lastly, it is often of interest for us to know the RMS value of the various harmonics as a proportion of the total RMS value. This example illustrates an instrument which measures this. Suppose you have a V of t which is root 2 times 100 sin omega naught t plus 20 times sin 3 omega naught t minus 5 times sin 5 omega naught t plus pi upon 6 minus 3 root 2 sin 7 omega naught t. So, we will stop with that up to the 7th harmonic. Now, we have an instrument which incorporates what is called a notch filter. We will explain the characteristics of the notch filter in a moment. So, this periodic non-sinusoidal signal is given to this notch filter. It can be connected to the notch filter. So, you have a switch here which can be thrown to either A or B. So, likewise here the switch can be thrown to either B or A, and this is connected to an RMS reading voltmeter. What this notch filter does is, this is the output V naught and this is the input V I suppose. It has a frequency response function h of j omega of this notch filter is it allows all frequencies, but cuts off any desired frequency. So, if this magnitude is 1, if this frequency is say omega x or omega naught in our case, that particular frequency omega naught is attenuated fully. If you introduce a sinusoid with that frequency, you get 0 output. All other frequencies come out unscathed without any amplification or attenuation. So, that is the characteristic of the notch filter. This appears to be like a notch, that is why it is called a notch filter. So, we have a notch filter like this. So, what happens is, if you put the switch on B, then the meter here, voltmeter, reads the RMS value of the input signal V of t. On the other hand, if you put the switches on A, both the switches on A, the fundamental is cut out and the meter reads the RMS value of all the other harmonic components, right. So, you have two readings in A and B, find readings of the voltmeter in positions A and B. In position B, it is VB, suppose the RMS value, that is the total. In position A, suppose you put this A, VA corresponds to the RMS value of the various harmonics. VB will be the reading corresponding to the RMS value of the input voltage. The ratio of VA to VB is said to be the total harmonic content of this the voltage, and suppose this is assumed to be sinusoid, this total harmonic content is said to be the total harmonic distortion of the sinusoid. So, this meter as such is called a distortion analyzer, and this is used to find out how a waveform which is supposedly sinusoid, how it gets distorted by contamination with various harmonics. So, you have suppose an amplifier system, you feed an input sine wave, the output also the amplified version must be a pure sine wave, but sometimes the amplifiers introduce distortion, and you would like to measure what is the amount of distortion that is caused by a device like an amplifier which may have some nonlinearities. So, this particular instrument which is called a distortion analyzer measures the harmonic distortion. This is called distortion analyzer. So, this distortion analyzer is essentially an instrument which measures the RMS value of the various harmonics as a ratio of the RMS value of the composite wave, or usually in practical cases this harmonic, the RMS value of the total wave is very nearly the RMS value, the fundamental. So, we can say it measures the RMS value of the various harmonics as a fraction of the RMS value of the fundamental as well.